And we will start with the semi-plenary talk from Sabri Koraltan from the University of Vienna in Austria. So Sabri completed his undergraduate studies and PhD at the University of Vienna under the supervision of Professor Dieter Suess. And his main scientific achievements are the development of magnetic sensors enabled by spin orbitors and the co-discovery of dipolar stabilized higher-order Skyrmions and Antiskyrmions. After a fellowship in Germany in the group of Prof. Manfred Albrecht, he has just now joined the University of Vienna again for his postdocs. So today he will tell us about dipolar stabilized Skyrmions and Antiskyrmions in Ferro and Ferrimagnetic Multilayers. Sabri, the floor is yours.
Perfect, thank you very much. So I will share this screen. I hope you can see it. I hope you can also hear me well.
Yes.
Perfect. Then small. Okay. So well, first of all, good morning, good afternoon, or good evening, wherever you are. And I would like to thank the organizers for the invitation, especially Silvia. And today I hope to tell you something about dipolar stabilized skyrmions and antiskyrmions, and mainly in ferro and ferrimagnetic multilayers. And this is some work that I've done in the past couple of years at the University of Vienna. So this is the outline of my presentation today. I would like to tell you something about topologically protected spin texture. We just look what this means and some examples, and in which type of systems you can find them, and then a very brief introduction into experimental and computational techniques, and then we will go right into the topic. So what it means to have antiskyrmions, for example, ferrimagnetic multilayers. So, as an introduction, we've already seen today many interesting talks on skyrmions, so I hope you are already a little bit familiar with it, but nevertheless, skyrmions can be described as, let me just take a laser pointer, can be described as topologically protected spin texture. So now let's assume that we have these two configurations, for example. So this can happen in a ferromagnet with a perpendicular magnetic anisotropy, which means that the magnetization outside here, for example, points down, and then we have a core, so we have a spin object. And inside the spin object, the magnetization points up, and then we have a domain wall enclosure, basically, which separates the inner core from the outer plane magnetized region. And we can have different type of skyrmions. So a topologically protected spin texture in this sense means that we have a spin object, which cannot be transformed into the uniform state by a continuous, let's say, into the ferromagnetic state by a continuous and uniform motion or force, which means the following. So we can take these skyrmions, for example, which are Bloch and air, and we can put them on the unit sphere. And if these are on the unit sphere, then it's going to be impossible to comb, for example, the hairs of this, or the spins of this hedgehog-like structure, to comb them into a ferromagnetic state. How do we differentiate between Bloch on the left and Nail on the right? Well, if we take now a cross section, so we take a chain of spins, then the domain wall at this location, it's a Bloch type domain wall. And on the right side, this would be Nail type of domain wall, and this also leads to the differences when we plot them onto the unit sphere. They can be found in materials in which the inversion symmetry is broken, mainly due to crystal structure or due to interface effects or spin-orbit couplings and so on. And this gives rise to the so-called Dzieloszynski-Moria interaction. So we will not discuss this type of skyrmions, but we will mainly focus on those that arise from the competition between the dipolar interactions and the perpendicular magnetic anisotropy. If we have a system with a strong, or let's say with a medium-high PMA, then the magnet or the spins would like to be aligned out of plane. So it either wants to be down or up. But the dipolar interaction, the demagnetization energy, would like to have something which is really demagnetized. So we want to build flux closure states. And in most materials, the compromise is then to build magnetic domains, especially at vanishing fields or at remnants. And when we now apply out-of-plane magnetic field, several scenarios can happen. And one of them is that we can have a stripe, a multi-domain state, and we apply a magnetic field. And then one of the stripes shrinks down and leaves behind one magnetic bubble or skyrmion. The second mechanism is that we can have a stripe and then we increase the out-of-plane magnetic field, and then this breaks down, it fissures or it collapses into multiple skyrmion states. And this can happen in different materials, so we can really have it in chiral magnets, for example, where we have skyrmion lattices, or we can also have magnetic multilayers. So this looks something like this. So we can start from a layer with a random magnetization state, and you apply out-of-plane magnetic field, and at the end you obtain a very high density skyrmion lattice because of fissure. Or we can have a stripe domain in which the domains are a bit larger, and then they shrink down into isolated stripes and eventually into small skyrmions. The research of skyrmions took a quite positive turn once the approach of using magnetic or ferromagnetic multilayers came into the play. And here in this work, what it was done is that we have two ferromagnetic layers, the iron and the cobalt, which are sandwiched between two heavy metal layers, the platinum and the iridium. And this gives rise each to a specific interface dissolution scheme reinteraction, so interface DMI, but on the ferromagnetic part, there is an effective DMI that acts. So we can, this also showed us that it's possible to use ferromagnetic multilayers to tune anisotropy, to tune density, and to tune the size of skyrmions, for example. And after this works, the work of Montoya from the Fullerton group, for example, has also shown that we don't even need DMI, actually. Ferrimagnetic multilayers might be enough. So what they did here is that they used iron gadolinium multilayers. So it's very thick multilayer system in which we have alternating iron and gadolinium layers. It's a gadolinium rich or dominated ferrimagnet, and at zero magnetic field we obtain a rich stripe phase, and we apply an out-of-plane magnetic field, and they collapse into a skyrmion lattice. And these are block type of skyrmions, so you can see that we have this rotation instead of this hedgehog-like spin texture. So this was the first case in which we saw this nice skyrmion lattice. And in further works, it was already shown that so we are not only limited to skyrmions. So the work from Stuart Parkin's group, especially by NIAC, they showed that they can use Heusler compounds. So again, it's a bit of engineering here because we basically combine different materials, and at the end we obtain a magnet in which we can tune the properties. And at the end, they found that in Heusler compounds, which have a D2D symmetry, the anisotropic DMI leads to the formation of anti-skyrmion. So what's the anti-skyrmion? If you look at the skyrmion above, this looks like a vortex. So I guess you're familiar with the vortex structure, so it's just a circulation. But the vortex is in plane, whereas the skyrmions are out of plane textures. And the anti-skyrmion is the topological counterpart to the skyrmion, and it has an anti-vortex-like structure. So the domain walls enclosing the skyrmion core, they follow this anti-skyrmion-like state. These are some of the spin textures that I will talk about, but I can also highly recommend this review article in which more spin textures beyond skyrmions are discussed. And we will also see that they have mentioned there's something, for example, which is called higher order skyrmion. And we will have a closer look at this towards the end of my presentation. Okay, which type of methods are we using for these works? Well, we will rely on magnetron sputtering to create our magnetic layers, so DC and RF magnetron sputtering. And we will use iron gadolinium-based multilayers, so ferrimagnetic multilayers, but as well as ferromagnetic multilayers, as I will show shortly. We do the characterization with squid VSM and ferromagnetic resonance. The nice part about this is that you can also obtain material parameters such as saturation magnetization using the squid VSM, for example, or the anisotropy constant using the ferromagnetic resonance when the NS is known. On the other hand, we need these two parameters to perform micromagnetic simulations, which I have heavily done during my PhD. And yeah, so we need these inputs basically from our experiments. And we will image the spin textures, and for this we will rely mostly on Lorentz transmission electron microscopy. So let's have a look what this means. What this means basically that we have a transmission electron microscope. So we have an electron emitter, and then we have the electron beam. So this is a very, let's say, schematic presentation, but the beam goes through lots of objective lenses and apertures, and then we have a grid, and this is, for example, a silicon nitride membrane with a thickness of 30 nanometers, and we spot a deposit on top of these membranes, and the electron beam can go through, and now the electrons experience a Lorentz force inside the material, and based on the magnetization, they can be deflected, so they will change their direction of movement, more or less. So at the end of the day on the image plane, we actually can obtain some superposition of the beams or some let's say concentration, deconcentration. Let's have a look what does it mean in terms of contrast. So we can have a magnetic state. So this is an up-down state, and all the magnetic domains in between, they point along the same direction. So they all point down in this case, for example. And when we calculate the LTM contrast for this specific magnetic configuration, we see that the domain walls are highlighted. So whenever we see that domain walls are highlighted, it means that the magnetization of the stripe, or like the domain walls of the stripe, they point along the same direction. If you have an achiral system, for example, so this one points up and then this one points down, then the domains themselves will be highlighted. In the case of some random distribution, then we can find both. So we'll have cases in which some of the domains will be highlighted, in cases in which some of the domain walls will be highlighted. And finally, if you have some sort of spin textures, especially lost Skyrmions, we can see them as bright or dark contrasts or circles. And the reason behind this is because the Skyrmions act as a lens. So they collect, for example, a counterclockwise Skyrmion, collects the electron beam, so collects the electron and acts as a lens, and we have an increased intensity. If you have a clockwise Skyrmion, of course, it depends on overfocus, underfocus, but if you have a clockwise Skyrmion, for example, then we have less intensity because the beam gets a bit. So for the first part, we are going to look what happens when we are using an iron gadolinium-based multilayer, just like Montoya, but with a small twist. Namely, we're going to introduce some iridium layers. So iridium is a material which is known, for example, to actually introduce interfacial BMI. So we're going to have some iridium insertion layers, and then we're going to see what happens here. This is some Lorentz-Stinian micrographs, again, taken at different magnetic fields, and you can see here that we have regions in which the domain walls are highlighted or in which the domains themselves are highlighted. And this tells us if we have a chiral or achiral stripes. Now we increase the magnetic field. And what we can see here is that the stripes will collapse into spin textures, and those that are achiral will collapse into trivial bubbles. And we can have certain spin objects here and here. And we could see that we have some Skyrmions and some anti-Skyrmions as well. So let's have a look. This is again the Lorentz-Stinian. And as we have previously discussed, if we have a counterclockwise rotation, then we have a bright spot. If it's a clockwise rotation, then we have dark spot. And a trivial bubble then looks like this. A trivial bubble, because it's topologically trivial. So you see that these the domain wall points along the same direction more or less. So now if we take a comb, we don't need a singularity. It's easy to enter the ferromagnetic state. And the fourth texture that we have seen there was the anti-Skyrmion. So we have discussed previously that I showed you that in the work of Nyack, there were anti-Skyrmions in these Oyster compounds based on anisotropic BMI. But what we see here is that in a ferrimagnetic multilayer, it's possible to obtain anti-Skyrmions as well. And if you look at this contrast, the way it's obtained, so we have like 4 half Skyrmions. So it's like, this is like 1 half of rotation, this is like 1 half, and this is the third and the fourth. And that's why we have here 4 different dots, and it means that the beam gets deflected here, collected here, and so on. So if you would have something which would have 2 more, so it's like dark, bright, dark, bright, dark, bright, right? This would mean that we have a second order anti-Skyrmion, as we could luckily, not luckily, but like uniquely image in this case. So we have something which has an additional iteration of narrative. Okay, so what did we do more differently, let's say, than the work of Montoya? So let's have a look what they first did. Well, they measured the saturation magnetization as well as the uniaxial anisotropy. They put it in a very nice phase diagram, and they said, well, here we have a Skyrmion lattice, here we have some isolated Skyrmions, and so on. So we took their data and we put it in our phase diagram. And then we took our data from our experiments where we saw Skyrmions and anti-Skyrmions. And what we see is that the iridium insertion layers will lower the saturation magnetization as well as the uniaxial anisotropy. So we enter a new phase pocket, let's say. And then we completed this with some simulation works. So, and then we obtained a more or less complete stability range of anti-skyrmions and skyrmions in this type of materials. And what we find is that there is a very well-defined stability range in which both can coexist. And we were exactly within the boundary of this region. Well, we are in this region, and we can see that they can indeed coexist. So we can have, for example, a block skyrmion, as also these two are block skyrmions, and we have first order antiskyrmion, second order antiskyrmions, and the trivial bubble, type 2 bubble. So, and the question is, are these really dipolar stabilized? And the reason behind that is because we had some iridium. And as I mentioned, iridium can lead to the formation of interfacial DMI. And here, what we want to do is that we actually did some micromagnetic simulations, and we tried to see if the DMI counteracts the coexistence, let's say, or the existence of anti-skyrmion. So we studied an anti-skyrmion, and we tried to check if it's still stable when we increase the DMI under different saturation magnetization. And we see that there is, again, a phase pocket, but also a DMI threshold below which the anti-skyrmions are stable in ferrimagnetic multilayers. The reason why we did this actually is because we measured BLS, so we measured brilliant light scattering, and there we found out that this sample shows a DMI of approximately 0.1 millijoule per square meters, and this is, for such a thick sample as we are using, it's actually quite high. So then we also checked with large-scale simulations if this is actually important at all. So what happens when we don't put DMI into the system, and then we put DMI into the system, and we find out that there is no real significant difference, let's say, between the two systems. So we can say that the skyrmions and anti-skyrmions are indeed dipolar skyrmions. How do they form? It's a bit different, like in the case of chiral magnets. So we don't have this anisotropic DMI. So the way it works here is that we have a tripod. So, and I would like to draw your attention to these two domain walls. So this one is dark, and this one appears to be bright. And at the center of it, we see here a bright spot. And this bright spot is a topological defect, and we will discuss this as well a bit later. So, and the way it works, we increase the magnetic field, and then some of the domains are shrinking, and eventually we are left with an anti-skyrmion. So we have provided again the simulations to it. So, and it's very well valid in simulations as well, and it's a similar process for skyrmions too. But what we see here, for example, let me go back, is that they appear quite randomly. So we want to find a way on how to control it. This is important for several applications. What we did here was that we used some vortices. So we have the blue layer, which is the skyrmion layer, as we had previously. And now we put some parmalloid disks and some parmalloid square lattices on. The reason why we do this is because in disks, we can then have, as the ground state, we can have a magnetic vortex. And here we can stabilize magnetic anti-vortices. What happens when we put these two together? Well, in our simulations, we actually obtain a full lattice of skyrmions as well as anti-skyrmions. So by using the vortices or anti-vortices, we can create three-dimensional topological textures, more or less, in which we imprint the skyrmionic states. And the nice part is they are stable. For example, when the vortex core points down and the magnetization outside points up, then a skyrmion can be obtained with the magnetization pointing as we thought. So now when we reverse the vortex core reversal, there is nothing that stabilizes the skyrmion underneath. And if you have a look at the work here, so we have the vortex core, which already switched actually. So they're a bit out of sync, as I see. So we have the black dot, we reverse the core, and eventually the skyrmion vanishes. So now we know that they exist, the antiskyrmions and skyrmions, we can control them. So let's also have a look if we can increase in which type of materials we can find them. And for this, we did something like this, that we combine different materials. So we have something with a low saturation magnetization and something with a high saturation magnetization. So if you remember the phase diagram, our goal is to move between this phase diagram, for example. So when we combine this, we can see that it's indeed possible to obtain some antiskyrmions bubble as well as skyrmions. We went a bit further and we wanted to have a ferrimagnet, a synthetic ferrimagnet, which means that we use now two ferromagnets instead of using a typical ferrimagnet, and we couple them anti-ferromagnetic. And then we can obtain, if these two are not compensated, we obtain a synthetic ferrimagnet. And what we found out is that we can actually stabilize what it looks like merons and antimerons. So we wanted to try this, but first we said, okay, let's just try a ferromagnet. So let's see that it doesn't work. And here we use cobalt nickel multilayers. And the cobalt nickel multilayer, it's a ferromagnet. It's used commonly for out-of-plane magnetized system because you can tune the bilayer number, for example, and you can obtain different properties. So it's a well-known system. The one thing that we did is instead of using the typical tantalum seed layer, we use platinum seed layer, which reduces the anisotropy quite a bit. And then we obtain split VSM loops that look like this. So you can see here that we have an opening. So we have a somewhat sheared hysteresis, but with an interesting opening here. And when we apply an in-plane magnetic field, then we also see an opening, which indicates that we have a large amount of domains. Then we also did some FMR characterization, so we saw in which range our saturation magnetization as well as anisotropy is. And this is actually way out of the range of our regular phase bucket that we had previously reported. We have some Lorentz TEM images taken at the University of Augsburg by Maria Massa and Alan Ulrich, and they saw these lines here. As you can see, there is bright spot or bright dot, dark dot, bright dot. So, and this looks awfully familiar, like those topological defects like we had previously. Well, after having all this characterization done, we performed some micromagnetic simulations, and we found out what these dots are. Well, these dots are vertical Bloch lines. So, and this is a region which is magnetized up. This is a region which is magnetized down. So we show the reduction map. And then we have the domain wall. And this domain wall has a certain orientation. And then we can see that it switches its orientation. So it's basically like a domain wall inside the domain wall. And when we have this vertical Bloch line, as it's called, at the zero field, we can apply now magnetic fields. And when we apply magnetic fields, we obtain a full new family of spin objects. Namely, this is the regular Bloch skyrmion, and this is the regular antiskyrmion, for example. We can have biskyrmions, which is a topological charge -2, or the second order antiskyrmions we have been reporting previously, but this goes on. So we can have -5, N5, and so on. And the reason why we can see this now in our simulations lies actually on the chosen discretization map. Because as I told you before, we have these vertical Bloch lines, which are a domain wall within the domain wall. And this, when we do the micromagnetic simulations, we need to resolve these smallest features, the vertical Bloch lines, and not the regular domain wall width. So in this system, the domain wall width is about like 6 nanometers. So when we use, let's say 3 nanometers, we already lose it. So we cannot actually find out the spin option. So we need a particularly small discretization length to stabilize. And when we compare, let's say this concept of higher order skyrmions with topology itself, I came up with a simple solution. So we can understand what it means to have higher order skyrmions. So consider now these donuts, consider now as topologically trivial. If you now take a cut here and we twist once, we have a Möbius strip. If we keep twisting it, we will obtain a higher order Möbius strip, which has an increased topological charge. And this is exactly how these skyrmions could work. So we have the skyrmions. If it rotates one, it's a skyrmion. If it rotates twice, then with clockwise, counterclockwise, then we have a biskyrmion, and so on. And with our experimental results, we can see that they can coexist. So we have different types. So this is a third order antiskyrmion, for example. This is a biskyrmion. We also have a 6th order. And in the simulations, they appear even more anywhere. So I don't have much time left. So let me show you some experimental comparison between isolated spin textures. So this is, for example, a fifth order anti-Skyrmion. As you can see, we have a very good agreement between simulations and experiments. And the reason they are actually forming is because the regular domain walls are less stable than the vertical block line. So when we apply the out-of-plane magnetic field, we can obtain the stable higher order Skyrmions from the vertical block lines. The nice part is that they can be moved by spin transfer torque. And if we increase the topological charge, then they move without the Skyrmion Hall effect. Okay, and one last thing that I would like to show you is can we image them with an alternative technique? And for this, we are doing high resolution MFM, so we go something very similar. I can skip this, but the idea is that again we have very nice anti-Skyrmions, and we did some MFM, high resolution MFM at EMPA, and you can see here that we actually see some dots in the MFM itself. And when we apply a magnetic field, we see isolated objects. And a brief comparison allows us to see that we can actually use magnetic force microscopy to image vertical block lines, Skyrmions, and for the first time also anti-Skyrmions based on the shadows, based on the straight field that the anti-Skyrmions and higher order anti-Skyrmions generate. With this, I would like to summarize my talk. So you can see that we can have Skyrmions and Antiskyrmions in both Ferrimagnetic multilayers as well as in Ferromagnetic multilayers. And I would like to thank everybody who was involved in all these works, and also to you for your attention, and briefly advertise for a job that we're offering right now as a PhD between Silicon Austria Labs and Technical University of Vienna, where I'm currently working. So if you know anybody, we would be happy to talk to you. So thank you again for your attention.
Thank you very much, Sabri. Now the floor is open for questions. We don't have much time, but please turn on your microphone if you want to ask something. I will start maybe with a quick question just to break the ice. So I think it's amazing that you can image all these different particles. But from the technological standpoint, so what are the main differences, and which one do you envision to be more useful? Do they interact differently with fields, with currents?
Yeah, so I didn't have much time to talk about this, but the one point that is actually the main difference, I would say, is so this is, for example, an anti-Skyrmion, the regular anti-Skyrmion, and as you can see, it moves in an angle. So this is the so-called Skyrmion Hall angle. So this happens to regular Skyrmions as well. So when you subject a Skyrmion racetrack, for example, to an electric current, they move in an angle. And what we found out is that if you increase the topological charge, so you go from 1 to 5, then the Skyrmion Hall angle decreases significantly. So for these type of applications where for the Skyrmion racetrack memory, for example, it's important that the Skyrmions move on a straight line. They could be promising there, but of course the entire concept has its flaws. In this concept, I think it could be a bit more advantageous. And one thing is, of course, that they are now offer more non-linearity. So when you want to excite them for any type of reservoir computing application, for example, you have an increased level of non-linearity. So I could think that maybe there a more robust signal could be obtained out of them.
I see. Thank you very much. So I think that in view of time, we have to skip to the next speaker, but maybe you can hang out in other town for if there are more questions.
Yes, perfect.
Okay.